Let's talk about rational exponents. For any real number a greater than 0, such that a doesn't equal 1, then a to the x is a unique real number. And we write a to the x, y equals a to the x is a function with domain negative infinity to positive infinity. If a to the b is equal to a to the c, then that means that b is equal to c. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. And if a is between 0 and 1 and m is less than n, then a to the m is greater than a to the n. So basically, if I raise a fraction to a higher power, it's going to become smaller. Now I can graph rational exponents. If I have my domain is just the integers, then I'm going to get these points that have this lovely shape here. Now, if I use rational numbers, I can see I get quite a few more numbers. And if I use all of the real numbers, I see I have a smooth curve that has this very distinctive shape. So if a is positive, then the exponential function with base a is said to be f of x is equal to a to the x. Now the restriction on a in the definition is really important. If a is negative, and say x is 1/2, then you're going to be taking the square root of negative numbers. So we're out of the real numbers realm. And if a is equal to 1, then the function just becomes a constant, and that's not an exponential function. So for 4 to the x, we need to find each of the following. F of negative 2 is 4 to the negative 2, which is 1 over 4 squared, or 1/16. 4 to the 5th is 4 times 4 times 4 times 4, which is 1,024. 4 to the 2/3, now you're going to want to rewrite this as 4 squared to the 1/3, which is 16 to the 1/3. And you can simplify this back down to 2 times the cubed root of 2. And then f of 2.15, well, that's just a calculator problem. 19.6983. So the exponential function is another function you need to make sure you know. When a is greater than 1, the domain is all reals. The range is from 0 to infinity. It goes through the points -1, 1 over a, 0, 1, and 1a. It has a horizontal asymptote of x equals 0. It's continuous and increasing for its entire domain. If a is less than 1, then the domain is still negative infinity to infinity. The range is still 0 to infinity. It goes to the point -1, 1 over a, 0, 1, and 1a. It also has a horizontal asymptote of x equals 0, but it is decreasing over the entire domain. Now this is just, it's kind of always interesting to look at a number of these. Suppose I have a to the x. These on the left side, starting over here, these are all when a is between 0 and 1. 1/2 to the x, 1/3 to the x, 1/10 to the x. You see they have all a very similar shape. They all go through 0, 1, and then they all come down to horizontal asymptote. Well, if if a is greater than 1, then this is f of x is 10 to the x, 3 to the x, and 2 to the x. Do you see the similarity between 1/10 to the x and 10 to the x? Be able to discuss in class what that relationship there is. Now, characteristics. We've already gone over these. The points -1, 1 over a, 0, 1, and 1a are on the graph. If a is greater than 1, it's increasing. If a is between 0 and 1, it's decreasing. It always has a horizontal asymptote of x equals y equals 0. The domain is all reals, and the range is from 0 to infinity. So what if I wanted you to graph y is 1/2 to the x? Always find the y-intercept is 0, 1 in this case. The x-axis is a horizontal asymptote. Make a list of points. You want to make points that are going to be easy to graph. Plot your points, graph your horizontal asymptote, and make a smooth curve. Now graph f of x equals -3 to the x. Give the domain and range. Now see, this is a reflection of 3 to the x across the x-axis. The domain is all reals, and the range is from -infinity to 0. Now f of x is 3 to the x minus 2. This is a horizontal shift to the right 2 units. So you can take 3 to the x and shift it 2 to the right. You still have a horizontal asymptote of y equals 0. Domain of all reals, and range from 0 to infinity. Now, if I wanted to graph 3 to the x plus 2 minus 2, this is a shift to the left 2 and down 2. So the horizontal asymptote is going to shift down. The domain is -infinity to +infinity, and the range is -2 to infinity. When we're doing exponential equations, there's a series of steps you need to follow. The first step is to isolate the exponent, or the exponential term. Step 2 is write each using a common base if you can. And then set the exponents equal, solve for x. And then you want to check. So 5 to the x is 125. I need to, first of all, use the definition of a negative exponent. So 1 over 125 is 125 to the -1. And now I need to rewrite 125 as 5 cubed. We're trying to get the common base. Since I had a base of 5 over here, I needed to get a base of 5 on the right. Now I'm going to use the power properties. So this becomes 5 to the -3. And now I'm going to set my exponents equal. So my solution is -3. Now suppose I want to solve 3 to the x plus 1 is equal to 9 to the x minus 3. The first thing I need to do is get a common base for the 9. 9 is 3 squared. So now I'm going to use the power rules. So this becomes, the left side becomes 3 to the 2x minus 6. Now that I have the same base, I set the exponents equal, and I'm able to solve for x. So x is equal to 7. So my solution set is x equals 7. Now suppose I want to solve x to the 2/3 is equal to 25. All right, I want to raise both sides to the 3/2 power, so that x is 25 to the 3/2, or the square root of 25 cubed. Square root of 25 is 5. So this becomes 5 cubed, or 125. It's necessary to check all proposed solutions when we have been raising things to powers. So when I put in x is 125, um, is 125 to the 2/3 equal to 25? Well, the cubed root of 125 is 5. 5 squared is indeed 25. So the solution set for this is plus or minus 125. Now, you do need to know this formula. You need to memorize this. Compound interest. If the amount in an account at any time t is going to equal the principal times 1 plus r, the interest rate compounded, n times per year, so r divided by n, to the nt, t times n. Now, remember, when we compound annually, that means n is going to equal 1, semi-annually is 2, quarterly is 4, monthly is 12, and daily, we're usually just going to use 365. So if $2,500 is deposited in an account paying 3% per year, compounded semi-annually, find the amount in the account after 10 years with no withdrawals. So you're going to need to write down your compound interest formula. I know that P is 2,500, R is 3 divided by 100, or 0.03, N is 2, and T is 10 years. So substituting this in, I'm going to have 2,500 times 1.015 to the 20th. We always, on money, round to the nearest hundred, so it's 3,367.14. These are pretty much always going to be calculator problems. How much interest is earned over the 10-year period? Well, the interest earned is the amount you started with, subtracted from the amount you have in the account. So that's $867.14. Brendan must pay a lump sum of $1,500 in 8 years. What amount deposited today at 2.4% compounded annually will give him $1,500 in 8 years? So write down your compound interest formula. Now you know A is 1,500 because that's what he's got to pay. His R is 2.4 divided by 100, or 0.024. N is 1 because it's compounded annually, and the time is 8. So the formula is 1,500 is equal to P times 1 plus 0.024 divided by 1 to the 8th. So P is 1,500 divided by 1.024 to the 8th, or the principal is $12,407.71. If he deposited that amount, he will have 1,500 when he needs it. Now, if only 12,025 is available to deposit now, what annual interest rate is needed for the money to increase to 1,500 in 8 years? Again, you go to your compound interest formula. Your principal is 12,025. And again, this is a calculator problem where you have to solve this for R. We're going to go into other methods for solving for R when we do logarithms, so don't stress too much about this one. When you compound continuously, let's look at what this means. So if n is 1, and I look at 1 plus 1 over n to the n, then that's 2. If n is 2, 1 over n, 1 plus 1 over n to the n is 2.25. If n is 10,000, 1 plus 1 over n to the n is 2.71815. And as you keep increasing n, you see it seems to be approaching a number that's about 2.718. And that turns out to be a very interesting number in mathematics, and that number is E. E is a very, very special number that appears naturally, and it's approximately equal to 2.71828, yada, yada, yada. It's too much for us to write, so we're just going to abbreviate it E. And you see that E is somewhere between, E to the x is somewhere between 2 to the x and 3 to the x, much closer to 3 to the x. When you compound continuously, A is equal to P e to the RT. So suppose $8,000 is deposited in an account paying 5% interest compounded continuously. So we know we're going to have E for 6 years. Find the total amount at the end of 6 years. So A is equal to PE to the RT. So when we substitute in, the principal is 8,000. The rate is 5 divided by 100, or 0.05, and T is 6. We get the amount is about $10,798.87. So let's compare some interests. Suppose 2,500 is invested at 3% into an account for 10 years. How much is in the account if we compound it quarterly, monthly, daily, and continuously? Well, quarterly means N is 4, so we get about $3,370.87. Monthly, N is 12, so we get $3,373.38. Daily, N is 365, so we get $3,374.61. And continuously, um, we use the P equals E to the RT formula, and we get $3,374.65. We're going to do a number of models that are exponential in nature, and they're always going to be of the form y is y naught e to the kt, where y naught is your initial amount of your substance or the initial population. K is your growth factor, or it's your decay factor, depending on whether it's positive or negative, and y is your value at any time t. So one example of exponential growth is a carbon dioxide. If current trends of burning fossil fuels and deforestation continue, then future amounts of atmospheric carbon dioxide will be increased as shown in the table. All right. The data can be modeled by the function y equals 0.001942 e to the 0.00609x. So what will be the atmospheric carbon dioxide level in 2015? Well, 2015, we're going to put x in for 2015 in for x. I get about 415 parts per million. Now use a graph of this model to estimate when the carbon dioxide will be doubled that what it was in 2000. So if you graph these, we see that carbon dioxide will be doubled in about 2012. This is very hard to see off the graph. The good news is we're not going to be doing these on a calculator, graphing calculator.